Optimization problems are application problems of this idea of finding a maximum and minimum. And I'm trying to use mostly problems in the business area, since that is what you're going to be working in for the most part. So in one of the things that if you're shipping out, or if you're wanting to store something in a box, let's say a business you want to maximize your volume, right, for your materials that you're using to make a box. So this problem, which comes from the textbook, and where you can find this is when you go into the content section of Folio for MyLab Math, there is a category called Multimedia Library. And in that library, you will find a PowerPoint presentation with a lot of examples from your textbook. It's kind of a summary of the textbook, and this is where I copied this problem. So let's take a look at this. We have a thin piece of cardboard, 8 inches by 8 inches, and we're going to be cutting out square corners of a variable length x. We're going to try and determine what is the length of x that we need to cut out of this material in order to form a box yielding maximum volume. So notice that if you fold after you cut these squares out and fold these sides up, you get a box like this. It doesn't have a lid, so obviously this is not going to be used for shipping, but here you have once you cut out a distance or a length of x from each side, so here's 1x, here's the second x, 2x is taken away from the total length of 8 inches. So we have 8 minus 2x is the length, and then the width also is 8 minus 2x, because we're talking about a square here, right? And when you cut those corners out and fold them up, this distance here is also x, because we're taking squares out. So these two sides are going to be the same. So that means the height, which is folded up, gives you x. So if you want to calculate the volume of this box, you're going to take the length times the width times the height. So if you want to get this for your notes, you're not going to have time maybe to copy it right now, but just go and check out that PowerPoint, and you can print it out if you want it to put in your notes. But here is the function that we're going to maximize. It's 8 minus 2x, the length, times the width, times the height. Just put a little note here, V equals length times width times height. Okay. We want to maximize our volume to get the most volume for our material that we're using. So the maximum is going to occur when the first derivative equals 0. But before I do that, let me multiply this out. And I did that earlier. Let's see where my notes are. All right. If you multiply this out, you get 4x cubed minus 32x squared plus 64x. And so taking the derivative of this, you're going to get 12x squared, right? 3 times 4 is 12, and then you subtract 1 from 3 to get the 2. Then 2 times negative 32 is negative 64x, and here the derivative is just 64. So here is our first derivative. We're going to set that equal to 0. And solving this equation, it's always good to simplify if you can, just to make your work a little bit easier. So my first step here is I'm going to multiply both sides by 1/4 because I noticed that 12 and 64 both have a factor of 4. And what I do to one side, I have to do to the other. So I'm going to get 3x squared minus 16x minus 16 equals 0. Now, this is a quadratic equation. So the first step is to try and factor it. And if you can't figure out how to factor it, you can always use the quadratic formula. If you will recall, the quadratic formula is minus b plus or minus the square root of b squared minus 4ac divided by 2a. So that's always going to work for you if you can't see how to factor it. But I was able to factor this, and you get 3x minus 4 times x minus 4. And if you FOIL that, you get 3x times x gives you 3x squared. Then you have minus 4 times 3x is negative 12x. Minus 4 times x is negative 4x. You combine those to get negative 16x. And your constant term comes from the negative 4 times the negative 4. And I made a mistake here. Let me see, where did I make my mistake? I copied this wrong. It's plus 64. So now negative 4 times negative 4 is 16. Okay. So once you factor it, then you can set each factor equal to 0. And so adding 4 to each side will give me 3x equals 4 here and x equals 4 here. And then for this equation, I want to divide out by 3. And so I get that x equals 4/3. Now this one simply is not going to work. And the reason is because you're taking out x from each side of the box, right? So if I take out 4 inches here and 4 inches here, the total length is 8. I'd be taking 8 minus 8, and I wouldn't have a box, right? So this value is not working. So 4/3 is going to work. And similarly, if you wanted to check the endpoints, because we have a function here and it ranges, x can only range between 0 and 4. So we already dismissed this one here. And also if it's 0, that's not going to work either. So it's going to be that middle value. And this 4/3 is approximately equal to 1.33 inches. And if the x is equal to 1.3 inches, so this is the height, the width, recall, and the length are both going to be equal to 8 minus 2 times 1.33 inches. And that is going to be 5.33 inches for each one. So the total volume, which is length times width times height, the maximum volume is 5.33 times 5.33 times 1.33, which is going to be 37.92, I think is what I got, cubic inches. That's your volume. Okay, So we found the dimensions and the volume by all coming from this critical point here, which will yield a maximum volume. Any questions on that one? Actually, I just looked at my notes here. It's 37.93. There we go. All right. So that's an example of an optimization problem. We want to optimize volume. And in business, often you're going to want to optimize things like profit. So let's look at another example, which involves the profit of a manufacturer of stereos. Any questions on this one before I move away to the next example? And there's one very similar to this problem in your homework. So we have a stereo manufacturer determines that in order to sell X units of a new stereo, the price per unit in dollars must be given by this function, P of X equals 1,000 minus X. The little p stands for price. And the manufacturer also determines that the total cost of producing X units is given by the cost function 3,000 plus 20X. And like I said, I got this off the PowerPoint from your textbook, and they had 2X in there, and I fixed it because the problem didn't make sense when it was 2X. I think that was a typo, and they meant 20X. So you might want to fix that if you end up printing out this problem for your notes. We have 5 steps that we want to go through. We want to find the total revenue, then we want to find the total profit, we want to maximize profit, and then we want to find the value of the maximum profit. And then we want to find out what price will yield this maximum profit. So those are the 5 steps of the problem. Let me go ahead and work through those. So we're given that little p of X equals 1,000 minus X. The cost function is given to us as 3,000 plus 20X. And revenue, so part A, we're looking for revenue. Revenue is the total amount that you're bringing in. And so if you have X, and I forgot to write this down, X is the number of units to sell. Okay. So the revenue is the number of units that you've sold times the price. So it's the price per unit times the number of units. So we're going to use R for revenue, and it's a function of X. The price is the 1,000 minus X. And then we're multiplying the number of units X. And that's going to produce minus X squared plus 1,000X when you multiply this out. And then switch the order. I always like to have it in standard order. And for standard order for a polynomial is you put the highest degree term first. So that's why I switched the order there. Okay, so this is our revenue function. Now, part B, we want to find the total profit. And for the profit, I'm going to use P, but I'm going to use capital P because I used little p up here. So the profit, which is going to be the revenue that the money that you bring in minus the cost that you put for producing the product. So profit is the revenue minus the cost. So this is going to be R of X minus C of X. So for our particular example, the revenue is this function here minus the cost, which is given to us. Notice I'm using parentheses. The reason why I'm using parentheses is because I want to subtract the whole cost. And so I need to distribute this negative to each term for the polynomial. So that means that P of X is going to be minus X squared plus 1000X minus 3000 minus 20X. And we want to combine like terms, so it's going to be minus X squared. 1000X minus 20X is going to be 980X. And then the constant term is negative 3000. So here's my function for profit. Now I want to maximize profit. So I've got my profit function, that's part B. Now part C is to maximize profit. So you're going to take your derivative and set it equal to 0. So if we subtract 980 from both sides, we get negative 2x equals minus 980. So now I'm going to divide both sides by negative 2. And that means that my x is going to be 490. And you'll notice that the second derivative, the second derivative here is negative 2, right? Here's the first derivative. If I take the derivative again, it's negative 2. This is negative, so that means it's concave down. So I can be rest assured that 490 is actually a maximum and not a minimum. I don't want a minimum profit, right? I can be rest assured that this is actually a maximum. All right, so the part D says, what is the maximum value of the profit? What is the maximum profit? So this isn't the profit, right? This is how we get the profit. This is the X. When we're asking what, remember, what is something that you're looking to the vertical axis for, which is your function value. Your vertical axis is the profit. So we have to plug this number into the profit function. And when we do that, we get $237,100. I'll let you plug that in. You're just taking this 490 and you're going to the original profit function right here. So you're going to take negative, and then you're going to take 490 squared and take the negative of that, add 980 times 490, and then you're going to subtract 3000. and this is what you get, 237/100. Okay. Finally, part E, we want to know what is the price that yields this maximum? What is the price, that yields this maximum profit? Well, X is 490. So remember, little p is the price. 1,000 minus X. So we're going to take 1,000 minus the 490. Whoops, sorry. When we take 1,000 and subtract 490, we get $510. So this is the price that we need to set in order to get this profit, which is our maximum. So it's a balancing act, right? If you set the price too high, not as many people are going to buy it. If you set it too low, you're not going to make as much money on the items. And so even though a lot of people may buy it, you're not making it, so there's a balancing point there. And that's because notice that our profit function is a quadratic function. And so it opens down. So you're going to have kind of a situation like this, right? Where if you're, and of course, at some point, when you have zero, if you sell zero, if you set your price too high, no one's going to buy it. That's one extreme, and the other extreme is setting the price at zero, and you're not going to make any money. So I mean, they're two extremes, and the ideal point is this maximum right there, which is achieved by setting the price at $510. Okay. Any questions on this problem? Okay. I'm going to skip example 3 in this in your textbook because it is dealing more with a biology thing, and I know you all are business majors, so I'm going to stick with business type questions. And I'm pretty sure that your homework, there may be, I don't think they have, I think they're all business problems in your homework. So I'm just going to skip example 3 and move on to example 4, where we have promoters of international fundraising concerts must walk a fine line between profit and loss, especially when determining the price to charge for admission to closed-circuit TV showings in local theaters. By keeping records, a theater determines that at an admission price of $26, it averages 1,000 people in attendance. So for every drop in price of $1, it gains 50 customers. And each customer spends an average of $4 on concessions. So what admission price should the theater charge in order to maximize total revenue? Okay, so there's a lot of information here, and we have to kind of sort it out. And by the way, there is a homework problem very similar to this. So it's good that I'm doing an example, because I think this is kind of a tricky problem just because there's so much going on. But let's boil it down. Whenever you get problems like this, you want to kind of map out how you're going to solve it. And so the first step is to simplify our information. And notice I underlined here the revenue. That's what we're shooting for. We want to maximize revenue. Well, how do you calculate revenue when you're talking about ticket sales? Well, you take the number of people that are attending multiplied by the admission price, okay? So plus you also have to include what you bring in for concessions, all right? So, so it says example 4, but it's actually my example 3 because we skipped example 3, but I'll just put example 4, skipped 3, so you know. And this is the ticket sales problem. maximize revenue. All right, so revenue. We want, how do we find the revenue? Well, it's equal to the ticket price. See, I'm not filling any details yet. I'm just writing out, kind of summarizing what it is that we're trying to find here. So we have ticket price times the number attending plus whatever we make from concessions. Concessions, okay? And we are given that the concession income is $4 for each customer that attends on average. So some people aren't going to spend any money and some people are going to spend more than $4. And so, but on average, each person attending spends $4. So this is going to equal the price times the number attending plus the $4 times each number, the number of people attending. Okay? So we have a common factor here, so we can write this as the price plus $4, right? We're combining the price and the $4 times the number attending. Okay, now the question is, what is the price? Well, it's not going to be $26, right? Because that's just a starting point. We are going to be dropping the price by $1 for, and it could be $1, it could be $2, it could be $3. It's just a variable. So our variable, the price depends on how much we're going to drop the price. How many times? In other words, how many dollars are we going to take off the price? And that's going to affect how many people attend. So as we increase the number of dollars that we take off the price, the people attending are going to increase by 50 each time. So the way we write that is we're going to have the price. It's going to be $26 to start with, but we're going to take off some variable amount. And then, of course, we're adding $4 for the concessions. Okay, and then the number of attending, would be 1,000. If we had 26, it would be 1,000, but for every X that we subtract, or for every dollar that we subtract off, so if we subtract X dollars, we're going to increase 50 times X in attendance. Okay, so you see how I'm working my way towards the actual math part? So our revenue then is going to be $30 minus X times 1,000 plus 50X. And if you multiply that all out, your revenue function works out to, if I can find my notes here, I think I got it, minus 50x squared plus 500x plus 30,000. So I just FOILed this to get this. And you can see if I have 50x times negative x, I get negative 50x squared. And then I have 50x times 30, that's going to be 1,500x, but then I'm going to subtract 1,000x, so that's the 500x. And then the constant term just comes from 30 times 1,000, that's 30,000. So there's my revenue. I want to maximize that, so I'm going to take the first derivative. I get negative 100x plus 500, set it equal to 0, and then I'm going to subtract 500 from both sides of the equation. So that means that x, negative 100x equals negative 500, and then I'm going to divide by 100 on either side of the equation. And so I get x equals 500. Okay? So, but let's get back to the question. The question is, what admission price should the theater charge in order to maximize total revenue? All right, well, the admission price, the price is the ticket price is 26 minus, oops, that's supposed to be 5. Negative 500 divided by negative 100 is 5. So 26 minus the x, which in this case is 5. So if I set my price at $21, I'm going to maximize my revenue. Okay, so that's how these problems work in section 3.5. Now let's go to the homework real quick. Since we have a little bit of time left, I hope. Looks like we have about 17 minutes. Oh, wait, yeah, 17 minutes left. That's good. All right, so we're working on section 3.4 and 3.5. And let's look at 3.5 since we're first. So there are only 10 problems. The first, let's see, 3 problems, or 4 problems. The first 4 problems, they give you a function. It's really not an application problem. So there are only 6 problems that are actually application problems. But these, there's something that may confuse you. So let me sort this out for you. So for example, here we have a function q equal x times y. Now, so far, all the functions that we have dealt with have had only one variable. And so in order to fix this problem, this one has 2 variables. You need to use the fact that x plus y equals 72. So you take this and combine it with this function. You're going to maximize q. And when you do that, you're going to get 1 variable for this function. So let me show you how to do that. Wait a minute, can you see it? I just realized that you might not be able to see that. Yep, as I was, okay, here we go. Sorry about that. So here's the problem. Here's the function q equals x, y, and x plus y equals 72. Like I said, this has got 2 variables in it, so I need to solve this and substitute it in here to cause my function to only have 1 variable. All right, so this is problem number 1 from your homework 3.5. And q equals x, y. That is called my objective function. And then the constraint is x plus y equals 72. So what you do is you solve for y in this equation by subtracting x from both sides, and you get that y equals 72 minus x. Then you take this function y and substitute it for this y here. So q equals x times 72 minus x. Now you can see we have one function in one variable. We can maximize this by taking the derivative, but first let me multiply this out. So I'm going to distribute this x here, and I get 72x minus x squared. And from this, finding the first derivative, we get negative 2x plus 72. I just kind of swapped the order. So I differentiated this term first to get the negative 2x, and then I differentiated this term to get the 72, set it equal to 0. Now I'm going to subtract 72 from both sides of my equation, and I get negative 2x equals negative 72. So dividing both sides by negative 2 gives me x equals 36. And if x equals 36, y equals 72 minus x, which is 72 minus 36, which is also 36. So if you want to maximize a product, the two numbers have to be the same value. And the constraint tells you what the sum of the two numbers is. So in order to maximize the product, the two numbers have to be equal. Okay. This is number 1. And the first 4 problems of this homework are all of this nature. You have to take your constraint. This is your constraint. Solve it for, let's say, y. I think in some of the problems you want to solve it for y squared because there's a y squared over here that you want to get rid of. Anyway, and then you substitute it into the other one, allowing you to maximize a function of one variable, not two. Okay. Now, before I leave the homework here, I want to do one more problem for you just to set it up at least. Oh, somebody has a question first. Oh, yes, about the screen. I think I fixed that. I hope I did. Yeah. Okay, thank you. Let's go back to the homework. And I will try to be careful to make sure you can see the problem. This is the one I wanted to set up for you. Let me double check and make sure you can see it. Looks like you can. Okay. A lifeguard needs to rope off a rectangular swimming area in front of Long Lake Beach using 1,100 yards of rope and floats. What dimensions of the rectangle will maximize the area, and what is the maximum area? Okay, like I said, I'm just going to set it up for you. We have 1,100 yards of rope. And let me see, what was that problem? Hold on. That was problem number 5. $1,100 yards of rope. So you've got water along a beach. So let's say this is the beach. And the lifeguard is taking the rope and setting up a swimming area. Oh, I already wrote that, 1,100 yards of rope. So the question is, what dimensions should we have for the buoys? You see, these are the buoys here that are holding the rope. Where are we going to position those? I suppose buoys wouldn't work, would they? That thing would float all over the place. I think you'd need like posts that you would secure. Anyway, whatever. So we have X, Y, X. Okay. This distance, X plus Y plus another X, has to be 1,100 yards. Okay. That's going to be your 2x plus y. This is your constraint. Obviously, in order to maximize area, you have to have a constraint. You can't just have infinite number of rope because then you would never have a maximum. It would just be infinity, right? Which is impossible. So you've got to have a constraint in order to maximize your function. So what are we maximizing? The objective function here is the area, which is x times y. So notice it's a function, xy. And it's a multivariable function. Okay, but we don't want a multivariable function. We can't maximize that, so we have to use our constraint and make a substitution. So if 1100 is equal to 2x plus y, and I subtract 2x from both sides, I'm going to get y is 1100 minus 2x. So I'm going to take this and replace this y here. So now my function is a function of x alone. And so a of x is going to be 1100x. I'm distributing this, right? 1100x minus 2x squared. And so I always like to write this term first, so I'm going to write it like this. So now I maximize this, so I take the derivative, etc. I'll let you guys finish it, okay? You set that equal to 0, etc., etc., okay?